What's up, everybody? In this video, we're going to learn how to do USACO 2018 February at the silver level. Problem number 1, rest stops. All right, let's read it together. Farmer John and his personal trainer, Bessie, are hiking up Mount Van Couver. Okay, Farmer John and Bessie are hiking up Mount Van Couver. For their purposes and yours, the mountain can be represented as a long, straight trail of length L meters, where L is between 1 and 10 to the 6th. 10 to the 6th, make a note of that. It means that we can't do O of n squared. If we do O of n squared, then that's going to be 10 to the 12th power, which is going to be way too big. Anything over about 10 to the 9th, we can't do. So file it away, that's going to come up later. Farmer John will hike the trail at a constant travel rate of RF seconds per meter, where RF is between 1 and 10 to the 6th. Okay, let's pick that apart a little bit. So RF seconds per meter. It's important to note that that's how many seconds there are for them to travel a meter, which means that 1 is the smallest value. The fastest they can possibly travel is 1 meter per second. And the slowest they can travel is 1 meter every 10 to the 6th seconds. So we're working with some pretty large numbers here. We may end up needing to use a long data type for those of you that are used to Java and C++. I'll check it out again in a little bit, but because of the size of these numbers, I'm thinking maybe an int is going to be too small. Okay, since he is working on his stamina, he will not take any rest stops along the way. Okay, so John is not going to stop no matter what, and we are going to get some rate, RF, which is how many seconds it takes him to travel 1 meter. So for example, if RF was equal to 3, that means it takes him 3 seconds to travel a meter. If from beginning to end, the total distance was 10 meters, I'm expecting that to take him 30 seconds. It'll be 3 seconds to get to the first spot, 3 seconds to get to the second spot, and so forth. And just as a heads up, fractional times do need to be counted. We can't just be exactly stationary and then after 3 seconds jump to the location. We will be traveling past that. Bessie, however, is allowed to take rest stops where she might find some tasty grass. Of course, she cannot stop just anywhere. There are n rest stops along the trail with 1 to 10 to the 5th. Again, 10 to the 5th, we can't square that. So just watch out for that. That's going to come up again. The ith step is xi meters from the start of the trail and has a tastiness value of ci. Let's read over that one more time. There are n rest stops, and the ith, I out of n, so we have so many stops, I out of n total stops with n rest stops. The ith stop is represented by xi meters from the start of the trail, which is like where it's located in terms of x, between 0 to L, which means we could have a rest stop at the very beginning. We'll have to watch out for that. Or no, we can't. It's greater than 0. So, okay, so it's got to be at least, sometimes they do greater than equal to. It's got to be between 1 and L minus 1, essentially. We could have 1, we could have L minus 1, but we can't have 0, we can't have L. So we're going to be describing these based on the xi, which is the position, and the tastiness value ci, which is going to be between 1 and 10 to the 6th. That's how tasty it is. If Bessie rests at stop I, which would be at xi with a tastiness of ci, for t seconds, sometime t, she receives ci times t tastiness units. So it's going to be t times ci. Essentially what that's saying is, if the tastiness is 4 and we're stopped there for 3 seconds, we're going to get a total of 12. That's going to be our tastiness score for that stop, that 3-second stop at that location with a tastiness of 4. When not at a rest stop, Bessie will be hiking at a fixed travel rate of RB. Okay, so we have RF up above. We're going to have RB down here. Seconds per meter again, with 1 less than or equal to RB, less than or equal to 10 to the 6th. So it could be 10 to the 6th, could be 1, could be anywhere in between. Since Bessie is young and fit, RB is strictly less than RF. RB is less than, not equal to, RF. And if you remember, this is the rate of Farmer John. Now, it's important to note that this does not mean that Bessie is traveling slower. It means that it will take fewer seconds for Bessie to travel 1 meter than it will take for Farmer John to travel 1 meter, which ultimately means Bessie is faster by definition. Bessie would like to maximize her consumption of tasty grass, but she's worried about Farmer John. She thinks that if at any point along the hike she is behind Farmer John on the trail, which shouldn't happen if you think about it, because she's faster. So if she's faster than Farmer John, but if at any point she's behind him, he might lose motivation to continue. Okay, that's important to note, because that means that if there was a really tasty spot right here, for example, say tastiness 4, and Bessie gets to this spot, and the ending is like way down here, even if Bessie is much faster, Bessie is not going to be allowing Farmer John to travel past that spot while she's still here. Even if she knows she can make it to the finish before he gets there, that still is not allowed. And additionally, as soon as Farmer John reaches this location, Bessie has to leave immediately. It's not going to be when Farmer John reaches the next meter. It's as soon as he reaches the spot. If he goes even 1 second past that, then Farmer John will be considered to be ahead, even though it hasn't been enough for him to move a full unit yet. We do have to keep track of fractional units. So as soon as Farmer John arrives, Bessie needs to depart. Help Bessie find the maximum total tastiness units she can obtain while making sure that Farmer John completes the hike. So basically what's going to happen is she's going to be racing forward trying to find tasty grass locations and then parking at them, eating until Farmer John catches up, and then departing as soon as right afterwards. All right, let's look at the input format. Input format is going to be from a file called reststops.in. You'll need to make a file reader for that. Also means the output is going to be to a file, reststops.out. The first line of input contains 4 integers, L, N, RF, and RB. So remember, L is the length of the trip up the mountain. N is the number of rest stops that there are. RF is how many seconds it takes Farmer John to travel 1 meter, and RB is how long it takes Bessie to travel 1 meter. So that's your first line. So here, for example, in the sample input, I've got a 10-meter long trail. There are 2 rest stops. Farmer John takes 4 seconds to travel 1 meter. Bessie takes 3 seconds to travel 1 meter. The next N lines, remembering that N is the number of rest stops, the next N lines describe the rest stops. For each I between 1 and N, means for every rest stop between 1 and N, the number of rest stops, the I plus first line, this is the first line of the file input. This is 2, which is the I plus first line. The I plus first line contains 2 integers, xi and ci. So for example, 7 would be x, x1, I guess in this case. And then 2 would be ci. So this indicates that there is at location 7, let's start drawing this out. So we've got a path, it's 10 meters long, 0 to 10. Farmer John is going to be up here. Bessie, let's go ahead and put Bessie down here. There is a tasty stop at 7 with a tastiness of 2. Put that in parentheses. And there is a tasty stop at 8, or there's a rest stop at 8 with a tastiness of 1. Okay, so it is guaranteed that RF is greater than RB. I think they mentioned that already, but we know for a fact that Bessie is faster. And 0 is less than x1, is less than x2, 3, 4, up to n. That tells us these are in sorted order, I believe, which is less than L. Yeah, that tells us it's in sorted order. So we don't need to worry about sorting these rest stops according to this input. Note that RF and RB are given in seconds per meter. Yeah, we covered that, but this is a really important thing to note. It's not meters per second. All right, output is a single integer, which is the maximum total tastiness of units that Bessie can receive. So in this example here, their output was 15. Let's try and plug that in and see if we can get the same answer. Clean this up a little bit. All right, so remembering that Farmer John is going to travel 4 seconds per meter. Farmer John, 4 seconds per meter. Bessie is going to be 3 seconds per meter. So until the first rest stop, there's nothing to do. So let's just have him go until Bessie reaches the first rest stop, and then we'll see what happens after that. So Bessie goes 3 seconds per meter. So at the 3 second mark, Bessie is going to be at the 1 meter mark. We'll say Bessie and Farmer John. Bessie will be at 1. Farmer John still will be at the starting point. Although again, we don't necessarily have to keep track of the fractional units. We do have to consider that by 3 seconds, he is past the 0 mark. He's actually at 0.75. we'll go ahead and write that with a decimal just to make sure we're keeping track of that. When you're actually doing the solution, we don't necessarily have to keep track of these units at all, but just for the sake of processing it. At the 4-second mark, that's when Farmer John is going to reach 1 meter, at which point Bessie will already be 1/3 of a meter past that, so 133. At meter 2, meter 2 will be reached by Bessie at time 6, at which point Farmer John will be, what is that? 6 and 4, 1.5, 1.5. At time 8, Bessie would be at 2 and 2/3, whereas Farmer John will have reached meter 2, and so forth. So you can kind of see the pattern here. If you want to know the time it takes Bessie to reach a certain position, for example, 7, we would just multiply 7 by her time, and then we would get 21. So let's go ahead and skip ahead to 21. At 21 seconds, Bessie is going to be at meter 7. At 21 seconds, Farmer John is going to be at, what is that, 21 over 4, 5 1/4? 5 1/4. Okay, so now Bessie has reached this first rest stop. It has a tastiness of 2. She could skip it and go to this one, but this one has a lower tastiness score, so there's no motivation to do that. So she's going to stop here and start eating. And she will be able to eat until Farmer John reaches meter 7. Farmer John is going to reach meter 7, and then Bessie will still be there. That'll be at time 7 times the speed of Farmer John, which, as you remember, was 4. I'm going to write these up here. And 3, which will be 28. At 28 seconds, that's when Farmer John will catch up with Bessie. Now, that took 7 seconds from 21 to 28, which means I've got 7 seconds where Bessie has access to a tastiness of 2. So 7 times 2 equals 14. So Bessie already has 14 tastiness accumulated. At this point, she's going to have to leave, and she will reach 0.8. Let's see, 4 seconds after she departs. If she departs at time 28, or sorry, 3 seconds after she departs, then it'd be time 31. At time 31, that's when Bessie is going to get to position 8. Now, this doesn't line up exactly. So when you're because 8 times 3 is not 31, because she did stop. She has 7 seconds of eating time that she spent where she wasn't traveling. So you will have to figure out how to account for that when you're doing your final calculations. So at 31, we're going to be at 8. Farmer John then will be at 7 3/4, which means we have 1 second left, 32, before, where Bessie will still be at 8, before Farmer John is able to reach 8 and catch up. In that 1 second, we will have 1 second at a tastiness level of 1, because that's the tastiness level at position 8, tastiness level of 1. 1 times 1 equals 1, and that's 1 additional tastiness. So far, we've got 14 plus 1. At that point, there's no more rest stops. Bessie's going to finish out the hike. Farmer John's going to finish out the hike, and the total amount of tastiness will be 14 plus 1, which is 15. We're going to check back on here. And then sample output, you can kind of see it under the big mess there, 15. So that was, in fact, 15 seconds. So that came out exactly the way we hoped it would. Okay, let's try some other examples, because as I'm sure you can imagine, there's going to be some interesting things that occur when the rest stops are mixed up a little bit. When we did the earlier example, we had at location 7 a tastiness of 2, and at location 8 a tastiness of 1. But what would happen if location 8 had a tastiness of 4? And then let's have 10 be at the end. We'll do this one a little bit more quickly. So I have Farmer John here, I have Bessie here, and this is my 0 position. Bessie's going to go straight to 7, which is going to take 21 seconds. Because remember, she's going 3 and Farmer John's going 4. But Bessie's not going to stop here, because there is a better rest stop up ahead. Now, in order to know that, upon arriving at 2, Bessie has to look ahead to see what rest stops there are, to see if there's a better rest stop. And if so, then she needs to skip this rest stop. Now, I mentioned earlier about that n squared situation. And this is where this is going to become a problem, and I'll show you guys how to get around it. Because of the way the n squared works, if I were to have rest stops at, let's make a couple more lines here, 8, 7, let's put a 9, let's put a 6 and a 5. So let's say like we've got a 3, 4, 2, 5. Let's make that 6 actually. Well, let me think. Let's do 6 here. 3, 6, 2, 4. 3. let's do that to start with. Okay. Did it say, can we have duplicates of the tastiness levels? I think we can have two different spots with the same tastiness. Let me see. It says we're guaranteed that we're guaranteed that the X positions are increasing. I don't think there's anything that says that we can't have two different rest stops with the same tastiness though. Yeah, we didn't run across anything like that. Okay, so it is possible. It should be possible for us to have 3 in both locations. I don't think it would change the calculation because best you could just stop at that one or that one. But it is good to double check and think whether or not things like that are restricted. If things like that are restricted and they're not on this problem, but if you hit a problem where they are, there's a chance that that might be a hint as far as how to solve it. If we guarantee that every single location is unique, then it may be sensible to rearrange the data in such a way where instead of having 5 connecting to 3 with a tastiness of 3, I could have tastiness 3 along with the location that has the tastiness 3, and then tastiness 4 along with the location that has tastiness 4. We won't need to do anything like that in this one, but sometimes being able to flip your data around like that can be a really useful trick. Okay, so here's where the n squared thing is going to be a problem. When Bessie arrives here and has a tastiness of 3, she needs to look ahead to see if there's something with a higher tastiness further on down the line. In fact, she really needs to stop at the thing with the highest tastiness, which is 6. That'll be her first stop. After leaving, she will need to find again what is the next highest thing going this way, which is going to involve potentially checking all of them again. And in that case, it's 4. She then would need to check the next highest thing again. Now, the problem is this is putting us in n squared time. If we are, for every single location, needing to check every other location all the way to the end, and we have to do that for every single stop, potentially, because we don't know what's coming up later, potentially that's going to put us in O of n squared time. And we saw earlier that n was 10 to the 5th, I believe. Was it 10 to the 5th or 10 to the 6th? 10 to the 5th, right here. 10 to the 5th. Because n is 10 to the 5th, if we square that, we're at 10 to the 10th. 10 to the 10th is a giant red flag. This is sort of USACO's way of telling you that your algorithm is going to run too slow. There are a couple very specific exceptions where they state directly in the problem that you will have extended time or extended memory, but for the most part, you don't square 10 to the 5th. Okay, so because of that, we need a faster way to be able to look at, oops, that was a 6. We need a faster way that when we arrive here, we can know further on down the line whether or not there's anything that has that's a better stop. I'll give you guys a minute to think about that. Feel free to pause the video if you want to think about how we're going to solve that, and then I'll go ahead and tell you. All right, assuming you haven't figured out yet, or if you haven't, what we can do is we need a way that here we know for sure there's nothing better further down the line. The way we're going to accomplish that is actually by running through in reverse. Let me show you how we're going to do this. What's going to happen is we're going to make a single pass going from right to left, keeping track of what the best is that we've ever seen. So to start with, at the first or at the final stop, I guess, our best will be equal to 3. Now, what that means is that anything to the left of us that we encounter that is a lower number than our best, we would not stop at. And if you remember the example data, let me see, where is that? Here. Okay, so we had that 7-2 and that 8-1. Because of the fact that the 1, which was later, was smaller than the 7, that holds, because as of here, the best would have been 1, which means that if there's an earlier better stop, I'm not going to skip this stop to go to that one. But those were reversed, where I have a 1 here and a 2 here, and my best was 2. And as I work my way this way, if I hit a 1, I know I'm not going to stop here because there's a better stop later on. So let's look at how that's going to work for this example here. So my best is going to be 3 because, let me clean this up a little bit too. My best is going to be 3 because on the final stop it's 3, which means anything I encounter that's lower than 3 as I work my way to the left is not going to be a stop I'm going to use at all. So when I go to the next one, it's 4. I have to upgrade my best to 4, but that's okay. I will stop at both of these because I will stop at the 4 for as long as possible until I get pushed out, and then I'm going to go to the 3, and I can stop at the 3 as well. There's no reason to skip the 3 because there's nothing better after it. There's also no reason to skip the 4 because the thing after that isn't better. There's nothing better nothing better after it. When I get to the 2 is exactly is less than my best, which means I won't be stopping at the 2. So what I can do in order to keep that simple is I'll just set the tastiness to 0. If I set the tastiness to 0, then when Bessie arrives there, there'd be no reason for her to stop. And that's how we're going to let ourselves know not to use that stop. Proceeding to the 6, that means that the best is now 6. Proceeding to the 3 is lower than the best, which means I'm going to change that to a 0. We won't be stopping there either. Having now gotten to the end, now I can run my simulation from left to right. Slash to my 0. Now we can run the simulation from left to right. Anytime I hit a stop of 0, Bessie won't stop there. Anytime I hit any other number that's not a 0, Bessie will stop there and wait until Farmer John catches up. So let's kind of look at how this algorithm is going to work. And the other thing to watch out for is we don't want to check every single X position. I can't think of any reason why you would do this. But do set up your data in such a way. We're not going to have, what did it say the L was? The L value was up to 10 to the 6th. Here, the L value is 10 to the 6th. You probably should not be making an array with a size of 10 to the 6th. You're going to want to find a cleaner way to do that. If you're working in Python, that might mean a list of tuples. If you're working in C++, that could be a list of pairs. If you're working in Java, probably if I was working in Java, I would have a pair of array lists where one of them represents the position and one of them represents the tastiness. And then I would just make sure to add the tastiness to one and the position to the other. Probably would be the best way to do it. Can't think of any reason to use a linked list. Yeah, an array list probably would be the easiest way to do it in Java. But yeah, you can think about, there's other ways to approach it as well. But do be thinking of ways to not have to brute force every possible location from 1 to 10 to the 6th. We don't want to have an array where most of it is empty, and we don't want to try and use, I guess a hash table would work. We don't want to do a hash table because then we'd have to check every single location, and we would want to, I guess you could get a list of keys. Anyway, yeah, probably your best bet there is going to be a list of pairs, list of tuples, or a pair of lists. Okay, so once we have that figured out and we zero out all of those individuals that we know we're not going to stop at, so then Bessie's going to go straight to the first one. So we look through, find the first thing that's numbered. Bessie will go straight there. From Bessie's current location, Bessie starts at 0. Farmer John starts at 0. For Bessie to go from 0 to 6 is going to be a total of 6 times 3, which is 18 seconds. For Farmer John to go from 0 to 6 is going to be a total of 4 times 6, which is 24 seconds, which means I have 24 minus 18, which is 6 seconds. And I'm going to have 6 times 6, which is 36, because the tastiness here is 6. So 6 times 6 is 36. That's going to put me at 24 seconds. If I have a time variable somewhere, t equals 24. And now Bessie and Farmer John are both at 6. I will find the next location, which is here, location 8. I know that the difference between 6 to 8 is 2. So what I can do is say, okay, well, the time it's going to take Bessie to travel from here to here is going to be 6 seconds. And the time it's going to take Farmer John to travel from here to here is going to be 8 seconds. Now, if you're keeping track of that, what that means is that we don't have to actually really keep track of the time. We just have to keep track of the distance between the two. And we can look at the time distance between these two to figure out how many seconds that is. Because of the fact that Farmer John is 1 second slower, if I go from 6 to 8, rather than trying to calculate what time I'll reach that 8, which you could do that, and that will run in about the same time complexity, but it may be easier for you to think about it in terms of, okay, we're going from 6 to 8, that's a difference of 2. In order to find out how much time that's going to give us, I'm going to multiply that by the difference in their 2 speeds. Farmer John at 4 seconds, Bessie at 3 seconds, which is going to be a total of 2 seconds. And that should mean that then Bessie's going to get 2 seconds to graze at this location. If you do it this way, then we don't have to keep track of the time. We really just have to keep track of the difference. So let's look at what that difference calculation is going to look like. And this will be the last optimization. So, okay, we have, let me just go ahead and write this out as 2 arrays. So I have an array that's going to be like 0, 6, 0, 4, 3, 2, and then potentially these are tuples or it's a separate array. This is going to be the locations 5, 6, 7, 8, 9, 10. And again, if you're on Python or C++, might want to put these as pairs or tuples. So it'd be 0, 5, 6, 6, and so forth. Okay, so we know the difference if we make the difference in the two, let's do Farmer John's speed, or what was it, RF? Let me write that using the correct notation. RF minus RB. If we calculate RF minus RB, we get the difference of their speed that's equal to 1, which means that for every meter, we're going to get 1 second, essentially. If Farmer John was at 5 and Bessie was at 3, then for every meter, we would get 2 seconds for every meter they travel. So walking through here, I find a 6. The last location I had was 0, so I'm just have like L equals 0. So when I get to the 6, I know that 6 minus 0 times the difference is going to be 6 seconds. I'll multiply 6 seconds times 6, and that gives me that 36 that I did earlier. That's the same number. I then proceed forward to find the next thing that's not a 0. That's this 4 right here. That's at time 8. I will update my location to, I forgot to do this. I'll update my location to 6 when I find that 6. Now I have this 8. I'll do 8 minus 6 times distance, times the difference, which is going to be 1. So 8 minus 6 is 2, times 1 is 2, and that'll be 2 seconds at a tastiness of 4, which will be 8. Let's write that 8 down. Next one that's not 0 is going to be here. That's at position 9. I need to update my location to 8. I find the next one at location 9. 9 minus 8 is going to be 1 meter traveled. Difference in speed of 1 second per meter. We're going to have then 1. We multiply 1 by the tastiness, which is 3, and that's going to be a 3. So I've got my 36. I've got my 8. Now I've got a 3. Final from 9 to 10. That's also a distance of 1. My previous distance being 9, or my previous location being 9. 10 minus 9 is 1, times the difference in speed, which is 1, times the tastiness, which is 2, is going to give us 2 tastiness. So for this example, we should have 36 plus 8 plus 3 plus 2. I'll cut you loose to code that. But remember, the key to this is however you decide to store these, we need to make one pass going from right to left to remove any stops we know we're not going to use. Once we know we're not going to use a stop, we can just zero it out. And then as we're then processing from left to right, anything that's not a 0, we know we're going to stop there. And the amount of time we're going to stop there is basically going to be whatever the distance is minus whatever the distance of the last stop is, remembering to start that at 0. Whatever that difference is, multiplied by the difference in how fast they're traveling will give us the number of seconds, multiplied by the tastiness at that location will give us the total tastiness we need to add together. All right, good luck coding it, and I'll talk to you in the next video.